Today we are going to learn an important subject of GATE exam, that is electronic devices and circuits, EDC. This subject carries around 4 to 6 marks in GATE exam out of 100, and also this subject is uh, important as far as analog electronics is concerned, because most of the topics in analog electronics are based on the concepts of EDC. We will start our discussion with energy band diagram. An energy band diagram is the representation of energy levels of different type of charge carriers that are present in the material. Charge carriers are of two different types. One is electron and one is hole. Electrons in the material are of two types. One which can take part in conduction, means after applying supply to the material, electrons can move, that are called free electrons. And another type is bonded electron. Bonded electron means which are in covalent bonds, or any other, in case of metal, in metallic bond. Bonded electrons which cannot move uh, even if we have applied supply across the material. And another type of charge carrier is hole. These three charge carriers carry different energy, means these are at different energy levels, and representation of energy of these charge carriers is done through energy band diagram. An energy band diagram basically consists of three energy band, one called conduction band, one valence band, and an energy band which separates both conduction band and valence band, called forbidden band. Conduction band means higher energy levels, valence band matlab means lower energy level, and forbidden band separates these lower energy levels and higher energy level. If an electron is bonded, means that cannot move, is said to be present in valence band, means valence band represents energy of bonded electrons. If we want this electron to take part in conduction, uh, we have to first move this electron from valence band to conduction band, means we have to break the covalent bond and make this electron as free electron. So now I can say that the energy of bonded electron lies in valence band, and the energy of free electrons lies in conduction band, means conduction band represents energy of free electrons present in the material, and valence band represent bonded electron present in the material. If this bonded electron is moved from valence band to conduction band, there will be a deficiency of electron which is called hole. This deficiency will remain in valence band itself. So now I can say that the valence band represent energy of holes present in the material. So there are three energy bands. First, conduction band. Conduction band. This conduction band represents energy of free electrons. Free electrons means the type of electrons which can move with when supply is given to the material. Number 2, valence band. Valence band represents represents energy of bonded electrons and holes in the material. Number 3, called forbidden band. Forbidden band is the separation between conduction band and valence band. If suppose any electron is present in valence band means an electron in valence band means it is a type of electron which cannot move even if supply is given. If this electron is if we want this electron to take part in conduction, we have to first move this electron from valence band to conduction band, and for this we have to supply some energy to the material. Energy is supplied in two form. Number one, we can increase temperature of the material, means surrounding temperature of the material, and number two, by making light to incident on the material. In these two form we can supply energy to the material. If temperature is increased of the material, we can say that energy is being supplied to the material, and with this energy supplied, an electron will gain some energy, and if it is sufficient to break the bond in the material, this electron will break the bond and will move from valence band to conduction band and become free electron. And the deficiency of electron in the valence band is called hole. To move an electron from valence band to conduction band, we have to supply some energy, which is approximately this much. This energy band which separates valence band and conduction band called forbidden energy band, and the width of forbidden energy band Eg represents the minimum energy required to be supplied in order to move an electron from valence band to conduction band. Now we will see energy band diagram for different materials. We will start with conductors, means metals. In case of metals, conduction takes place due to only electrons. Means there are no holes in case of metals. Also, metal possess one property, that the electron concentration, I'm talking about free electrons only. Electron concentration is independent of temperature. Means if we are increasing temperature of the material or decreasing temperature of the material, it will not have any effect on electron concentration. Means there is no bond breaking process in case of metals. So electron concentration will be same at 0 degrees Kelvin, or at room temperature, or at 100 degrees Celsius. At all the temperatures the electron concentration will be same. So I can conclude that in case of metals, to make any electron free, I need not supply any energy. That is, in case of metal, conduction band and valence band are not separated by any forbidden energy band, that is forbidden energy band gap. Eg is equal to 0, and Eg is represented in electron volts, energy of unit of energy, electron volts. Eg equal to 0 electron volts for metals, means we need not supply any energy to the metal in order to obtain conduction from metal. Number 2, semiconductors. Semiconductors are the materials which sometimes conduct, means depending on the surrounding condition, and sometimes do not conduct, behave as an insulator. In case of semiconductors, both electrons and holes take part in conduction, means there are electrons and as well holes are charge carriers in case of semiconductors. In case of semiconductors, if we change the surrounding temperature, means energy is supplied to the material, the electron and hole concentration will change with temperature, means bonds will be broken and more number of electrons and holes will be generated with increase in temperature of the material. In case of semiconductors, the energy band diagram consists of all the three bands, that is conduction band, valence band, and a band which is separating both valence band and conduction band called forbidden band. The lowest energy of conduction band is called energy level EC, and the highest energy of valence band is called EV. And these EV and EC are separated by forbidden energy band whose width is represented by EG. For semiconductors, Eg is not equal to 0 volt and it is around 1 electron volt at room temperature. At T equal to 0 degrees Kelvin, in case of semiconductors, T equal to 0 degrees Kelvin means no energy is supplied from the surrounding surrounding means material is not supplied with any energy from the surrounding, and in this case in a semiconductor all the electrons will be in bonds, that is bonded, and these bonded electrons will be present in valence band. If all the electrons are in valence band, there will be no electrons in conduction band. As there are no free electrons, I will say there are no electrons in conduction band, means conduction band is empty for semiconductors at T equal to 0 degrees Kelvin. 0 degrees Kelvin means absolute zero, or or it is minus 273 degree Celsius. At this temperature, there is no energy supplied to the material and all the electrons will present in valence band, means valence band will be completely filled. All the energy bands, all the energy levels will consist electrons, means all the electrons are in valence band and all the energy bands in conduction band will be empty. and this energy band which is separating valence band and conduction band have width Eg nearly 0.785 electron volts for germanium material, and it is around 1.21 electron volts for silicon. So at T equal to 0 degrees Kelvin, at a T equal to 0 degrees Kelvin, if we want to break any bond in case of semiconductors, we will have to apply an energy that is equal to Eg 0.7 0.785 electron volts in case of germanium, and equal to 1.21 electron volts in case of silicon. If this much energy is applied, we can easily break a covalent bond in the semiconductor material. If temperature is increased, energy will be supplied energy will be supplied to the material, and with these with this energy, if any electron in the material get sufficient energy to the if any electron bonded electron gets sufficient energy sufficient energy to break a covalent bond, it will break a covalent bond, and this bonded electron which is present in valence band will move from valence band to conduction band. If these kind of many electron break covalent bond, then after every covalent bond broken, there will be a deficiency of electron in valence band, and which will be shown by a hole, and the electron will be shown in conduction band. This electron which is in conduction band, it is an electron which is able to move when supply is given to the material. In conduction band, now we can see many electrons, means free electrons are now available for conduction, and there are holes available in valence band for conduction. And with increase in temperature, these charge carriers which are able to take part in conduction are increasing, and now we can say that with increase in temperature, the material will start conducting. At T equal to 300 degrees Kelvin, we already have increased the temperature of material, and at this temperature T equal to 300 degrees Kelvin, the additional energy required to be supplied to break more number of covalent bond, already there are some holes and electrons in the material which can take part in conduction, and if we want to break more number of covalent bonds, we will have to supply more energy. And now at this temperature T equal to 300 degrees Kelvin, the forbidden energy band gap becomes around 0.72 electron volts in case of germanium, and equal to 1.21 electron 1 point sorry 1.1 electron volts for silicon. Means the energy band gap Eg reduces with temperature. At a T equal to 0 degrees Kelvin, this energy was 0.785 electron volt. This much energy was required to be supplied in order to break covalent bond, and this energy was 1.21 electron volt. This much energy was required in order to break a covalent bond, and at a T equal to 0 degrees Kelvin, with increase in temperature, this energy reduces to 0.72 electron volt for germanium and 1.1 electron volt for silicon. Now we can conclude that with increase in temperature, the forbidden energy band gap decreases. That is, forbidden energy band gap Eg is inversely proportional to temperature, and its relation with temperature is defined as Eg at any temperature T in degrees Kelvin equal to Eg at 0 degrees Kelvin minus beta into T, where where Eg at T degrees Kelvin means forbidden energy band gap Eg at temperature T degrees Kelvin. This T can be any temperature, room temperature 500 degrees Celsius or whatever may be. Eg at 0 degrees Kelvin, it is the value of forbidden energy band gap at T equal to 0 degrees Kelvin. And for two materials, germanium and silicon, we know this energy is 1.21 electron volt for silicon and 0.785 electron volt for germanium. And beta is material constant. Beta is material constant, and the value of beta is around 2.2 into 10 raised to power minus 4 electron volts per degrees Kelvin for germanium, and equal to 3.6 into 10 raised to power minus 4 electron volts per degrees Kelvin for silicon. Now, with the knowledge of this equation, Eg at T degrees Kelvin equal to Eg 0 degrees Kelvin minus beta into T, we can now calculate forbidden energy band gap at any temperature T. For example, for example, we want to calculate Eg equal to what at T equal to 300 degrees Kelvin if Eg at 0 degrees Kelvin equal to 1.21 electron volts. Eg, we know that Eg at 300 degrees Kelvin will be equal to Eg at 0 degrees Kelvin minus beta into T. T is the temperature at which we want to calculate forbidden energy band gap, and it is 300 degrees Kelvin. Eg at 0 degrees Kelvin is given as 1.21 electron volt. Now we can calculate Eg at 300 degrees Kelvin equal to Eg at 300 degrees Kelvin equal to 1.21 electron volts minus beta. From this energy uh, we can conclude that this material is silicon, and for silicon this beta is equal to 3.6 into 10 raised to power minus 4 into this temperature T, which is equal to 300 degrees Kelvin. After we calculate this equation, we get Eg around 1.1 electron volt, which we have seen already. Means Ag at 300 degrees Kelvin is nearly 1.1 electron volt for silicon material. The third material is insulator. In case of insulator, they do not conduct at normal working temperatures. Means even if we have supplied energy to a material which is insulator, it will not conduct. Insulators do not conduct. The basic reason behind that is the forbidden energy band gap, EG, for insulator is nearly around 5 electron volt to 15 electron volt. This energy is very large as far as electrons are concerned. For electrons, this energy is very large, and this much energy is not possible to be supplied in order to make an electron free in case of insulator. So we can say that in insulator the forbidden energy band gap is very large, and this much energy cannot be supplied in order to move an electron from valence band to conduction band. Hence we can say that an insulator do not conduct. We have already seen about the three basic type of materials, that is conductor, insulator, and uh, semiconductors. Out of these three materials, will mainly focus on semiconductors because we are going to study the devices which are made up of semiconductor material. Semiconductors are classified into two types. One is intrinsic semiconductor. An intrinsic semiconductor is also called pure semiconductor. Pure semiconductor means in this semiconductor only the semiconductor atoms are present, that is there are no other atoms added to this material. The other type is called extrinsic semiconductor. They are also called impure semiconductor. Impure semiconductor means we have added some other atoms to the semiconductor. And a special case of extrinsic semiconductor called degenerated semiconductor. This degenerated word is used for the doped semiconductor, extrinsic semiconductor, in which doping is very high, doped highly. Doping means doping means addition of other impurities to the material. If a material is doped, it is called extrinsic semiconductor or called impure semiconductor. If doping is very high, then in that case a semiconductor is called degenerated semiconductor. A highly doped material is called degenerated semiconductor.